Okay, welcome back to the second lesson in chapter 2, which is on quantity of heat. So, in the first lesson, we talked about SHC, specific heat capacity, and now we're going to talk about specific latent heat. When we talk about latent heat, we're talking about changing the state of something. So I've got a situation here. Once again, think about that word, specific. That means I'm going to take a definite amount of something. And the amount we're going to take, as usual, is 1 kilogram. So I take 1 kilogram of ice and I put a thermometer into it. Now the temperature of ice is commonly assumed to be 0 degrees Celsius, but actually it could be -10, it could be -20. When I talk about ice being at 0 degrees Celsius, I'm talking about ice that is beginning to melt. Now here I've got some ice beginning to melt. It hasn't quite melted yet, and its temperature is 0 degrees Celsius. I'm going to add heat energy to it using whatever, a Bunsen burner or a hot plate. So energy goes into it. And as a result of that, eventually that ice will turn into water. But it turns into water also at 0 degrees Celsius. So the temperature hasn't gone up at all. So here I've been adding in heat into that system, and yet the temperature isn't going up. So in one sense, that energy is hidden from the thermometer. It's hidden or latent heat that we're talking about. Well, what happens to that particular heat energy? Well, if I had a little diagram of a solid. In a solid, you've got lots of atoms or molecules, and they're all tightly packed together. Now, they may be able to vibrate, but they actually don't move around the place. They stay in their same positions. As I heat them up, they start to vibrate more and more, and eventually get to a point where the bonds holding them in position break loose, and you have a liquid. And now you have a situation where those molecules are able to flow as a liquid would flow. So when I change from a solid to a liquid, all the energy goes into breaking those bonds apart. It doesn't increase the temperature of the water. So basically, if I put my hand in there, it'll feel the same coldness as putting my hand in there. Now, how much energy do I have to put in to 1 kilogram of ice to turn it into 1 kilogram of water without changing its temperature? Well, the experiments have been done, and the value is 330,000 joules of heat energy is required. Sometimes we write that down in scientific notation. I can work it out in my head, count 1, 2, 3, 4, 5. I can write that down as 3.3 by 10 to the power of 5 joules. That number is called the specific latent heat of fusion of ice. Kind of sounds a bit strange. I prefer to call it the melting of ice. Fusion of ice. Well, fusion, I suppose, is fusing together those liquid molecules to form a solid. So L, that value L, I need 3.3 by 10 to the power of 5 joules, and I need that for every single kilogram. That's per kilogram. kg to the power of -1. So that value there, that tells me how much energy I need to melt 1 kilogram of ice. Well, what about 2 kilograms of ice or 3 kilograms of ice? If it was 2 kilograms of ice, you would just multiply that number by 2. And as a result of that, I'm just going to literally multiply that number by the mass in question. So I get a nice little formula. The energy is the mass by the latent heat. That value is per kilogram. So there's another formula that we have. There's the formula that we had in the first lesson. And basically we use that formula anytime the temperature changes, but it stays in the same state. And what do I mean by states? Well, here are the states. S is solid, L is liquid, and G is gas. Anytime I change state, I'm going to use E equals ml. That's for a change in the state. Anytime I stay in the same state, but the temperature changes, like water gets hotter or a calorimeter gets colder, then I use this formula. So anytime there's a change in the temperature, theta, I use that formula. Now, of course, there's another change of state, isn't there? And that's where water changes into steam. Steam being a gas. Well, you know what the temperature of boiling water is, 100 degrees Celsius. And I add heat energy to that, and eventually I turn that into steam, and the steam is at 100 degrees Celsius as well. The temperature hasn't changed. I've put lots and lots of energy into it, and the temperature hasn't changed because I'm changing the state. Here's what a liquid looks like, where the molecules, they have a certain amount of movement. They're still stuck together, but they can move around each other. And when you turn something into a gas, you're giving those molecules complete freedom, so they can fly off in all different directions. In order to change from one state to another, I've got to give it energy called latent heat. Now, the energy I've got to put in here, once again I'm talking about 1 kilogram of boiling water, and I'm turning it into 1 kilogram of steam. The amount of energy I've got to put in there is 2,300,000 joules. That's a huge amount of energy. Which kind of brings me to an interesting point. Like if I stuck my hand into that water there, 100 degrees Celsius, I'm going to be screaming in pain. If I stuck my hand into steam, which is also 100 degrees Celsius, yeah, because they feel the same temperature, the same amount of pain, same kind of scream. But a number of minutes later, my pain over here will be far, far greater. And I'll tell you why. Because all of that steam there is condensing into your flesh, into your tissue. And we're talking about 2,300,000 joules of heat energy is being transferred into your body, which causes a serious amount of damage. So getting a steam burn can have far more serious consequences than getting a water burn, even though the temperatures are the same. Once again, you can turn that into scientific notation. 1, 2, 3, 4, 5, 6. So that's 2.3 by 10 to the power of 6 joules per kilogram. Remember what it means. I need 2.3 by 10 to the power of 6 joules to change 1 kilogram of boiling water at 100 degrees Celsius into 1 kilogram of steam at the same temperature. I'm changing its state. And the formula for that is E is equal to ml, but you have to be careful. What change of state am I talking about? If you're talking about ice, then I'm going to use that value. That's called the latent heat of fusion of ice. And if I'm talking about steam, I'm going to use that value. That's called the specific latent heat of vaporization of steam. So we've got two values depending on what state we're talking about. So I could write down here, I suppose, L ice and L steam is 2.3 by 10 to the power of 6 joules per kilogram. There is your formula. We have a definition. You know, on page 8, there's first of all a definition for what specific latent heat is in general. It's the energy needed to change the state of 1 kilogram of a substance. And then we have definitions for what is the latent heat of fusion of ice and what's the latent heat of vaporization of steam. But look, if I ask you for a definition of L, you can write it down as a formula. You can write down L is equal to E divided by M. But if you do that, of course, you have to write down what everything means and what their units are. Anyway, these formulae are in your table book on page 58. Right, let's do an example of it. Let's go to example 5, which is on page 9. It says, calculate the amount of energy required to convert 75 grams of ice. 75 grams of ice. What do I do immediately? I turn that into kilograms. I jump a decimal point at the end, 3 to the left, so I get 0.075 kilograms. There's two values for latent heat. The one I need to use, of course, is the latent heat of fusion of ice, whose value is 3.3 by 10 to the power of 5 joules per kilogram. Well, how much energy is required? That's easy. I'm going to use the formula ml. So E is equal to ml, which is 0.075 by 3.3 by 10 to the power of 5. Put that into my calculator. And I get an answer of 24,750 joules. That's a straightforward example. Now, remember in the last lesson we talked about specific heat capacity, and we had another kind of thing called heat capacity where the mass wasn't involved. Well, we do the same with latent heat. We have a thing called, instead of talking about the specific latent heat, which I call little l, we just talk about the latent heat. And we call that value capital L. So let's say, for example, I've got an ice cube. I don't care what its mass is. I just want to know how much energy do I need to melt that ice cube, to turn it from water at 0 degrees, ice at 0 degrees Celsius into water at 0 degrees Celsius. How much energy do I need? Let's say in this particular example, I need 1,000 joules. I don't care about its mass. I'm just saying to melt that ice cube, I need 1,000 joules. So we call that big L, and it's called its latent heat. And the formula therefore is E is just equal to big L. That's it. Whereas over here, you've got E is equal to ml. You need the mass, don't you? If you're talking about specific latent heat. Let's do an example involving this. First of all, they don't ask this very often. Occasionally. So let's do example 6. So it says, a company manufactures standard ice cubes used to chill water drinks when the cubes melt in the drink. A standard ice cube at 0 degrees Celsius. There's my standard ice cube. Its temperature, 0 degrees Celsius. It causes a drink of 120 grams. So the mass of the water, 120 grams. Change that into kilograms, 0.12 kilograms. It's at 10 degrees Celsius, and it causes it to chill by 1 degree Celsius. So it's at 10 degrees Celsius, and when I put the ice cube into it and the ice cube melts, the temperature of that drink falls to 9 degrees Celsius. That will be the final temperature of everything. Delta theta is 1 degree Celsius. Now I did highlight in this particular problem, in bold, it says when it melts. When it turns into water, the water may cool it down further. So I'm not going to take that into account here. I'm just talking about when it melts. Once again, what's my energy equation? The ice cube is going to melt, isn't it? It's going to be energy gained by the ice cube, and the water is going to get colder. So it's going to be energy lost by the water. They didn't mention anything about the mass of the ice cube. So the question they're asking me is, what is the latent heat? They didn't use that word specific, sure they didn't. And there's no mass anyway, so because no mass is given, I kind of know I've got to use this formula here, E is equal to L. So the energy gained by the cube is just given by L. The energy lost by the water? Well, I think I'm back to what we had here last week. I mean, the water, that's not changing state, that's just changing temperature. So I'm going to use mc delta theta for the water. So over here, it's going to be mc delta theta for W. Let's put my numbers in. Mass of the water, 0.12. The SHC of water is given, 4,180. And the change in temperature of the water, it was 10. It dropped by 1 degree to 9. Delta theta is 10 minus 9, or 1 degree. Actually, they just told me the one, didn't they? So that's an easy calculation. Just put those numbers into your calculator. And I get 501.6 joules. That's the latent heat of that ice cube. What's it telling me? It's telling me that I need 501.6 joules to melt those ice cubes. So they never mention the mass, it's just the ice cube in question. Look, we rarely use that formula E is equal to L. I mean, the formulae that we use all the time have the word specific in them, and therefore the M is involved. So it's E is equal to ML and E is equal to MC delta theta. So let's move on to example 7. How much heat is needed to change 1.8 kilograms of ice at 0 degrees Celsius? There's my ice at 0 degrees Celsius. And I want to convert that into 1.8 kilograms of steam at 100 degrees Celsius. So I want to go from there, ice, down to there, steam. I first of all want to change the ice at 0 degrees Celsius into cold water, also at 0 degrees Celsius. We're talking about a changed state. Look, we've got two formulae here. We've talked about it before. That formula, anytime we have a change in temperature. This formula, anytime we have a change in state. There, the state is changing. So therefore, the formula I'm going to use is E is equal to ml. Move on to the next stage. We're now talking about water, which is at 0 degrees Celsius. And we're talking about adding energy to raise its temperature to 100 degrees Celsius. Well, what formula am I using? I'm now going to be using the formula E is equal to mc delta theta, because we're talking about staying as water. We're not changing its state, we're just raising its temperature. So the formula I'll be using here will be mc delta theta. And then when I get down here, I'm now talking about changing the state again. So I've got hot water at 100 degrees Celsius. I'm now going to change it into steam, also at 100 degrees Celsius. So I'm now talking about, once again, E is equal to ml. But I suppose the difference in the two formulae, up here and down there, is that value of L is going to change. That L is for the fusion of ice, and this L is going to be for the vaporization of steam. So I just put my numbers in. By the way, the mass doesn't change all the way through. I mean, its volume might increase, but the actual physical mass of the ice doesn't change. 1.8 kilograms of ice gets turned into 1.8 kilograms of steam. So it's 1.8. I've got to use my values, so the constants are given there for the latent heat of fusion of ice. 3.3 by 10 to the power of 5. Now I'm talking about changing the temperature of the water. Its mass is 1.8 kilograms. The SHG of water is 4,180. And the change in temperature of the water, it was 0, it went up to 100, that's a change of 100. Finally, I now want to change the state of the boiling water into steam at the same temperature. So it's ml again. The mass is 1.8. But this L is now a different L to the previous L. That was for ice. This one is for steam. And its value is 2.3 by 10 to the power of 6. Basically, they're asking you for the total energy. So you're just going to add together 3 different values, put them into your calculator as they are. You do that calculation yourself. I'm going to check the answer. So the answer I get for example 7 is 5.49 by 10 to the power of 6 joules. Okay, moving on to a harder problem. I'm now on to example 8. I'm now going to do another mixing problem. We're now going to be mixing where we're now going to use both formulae together. So they can be a little bit tricky. So example 8. I've got 80 grams of ice at 0 degrees Celsius. The mass of the ice is 80 grams. Turn that into kilograms. And when I turn it into kilograms, I get 0.08 kilograms. I'm going to add that to 640 grams of water. So the mass of the water, MW, 640 in my head, 0.64 kilograms. The water at the moment is at 68 degrees Celsius. And you know what's going to happen when you put the ice in there? The temperature is going to go down. And it's going to go down to some final temperature. And that's the question. What is that final temperature? Don't know what it is, so I'm going to call it theta. I'm going to put a box around it because that's the final temperature of everything. The melted ice and the water is theta. So once again, I have my energy equation, which simply says 1 gains, 1 loses. Who gains? Well, the ice melts. So the energy gained by the ice. Who loses? Well, the temperature of the water is going to fall as a result of the melting ice. It's the energy lost by the water. Now, I've got to be careful. Energy gained by the ice, it comes in 2 stages. First of all, I have to melt the ice, and then I have to change the temperature of the water that came from the ice. The energy I need to melt the ice, that's called ml. So it's ml for the ice. Now I'm talking about the water that came from the ice. Because I'm changing the temperature of water, I'm going to be using mc delta theta. It's going to be mc delta theta. That's for the ice. Even though it's no longer ice, if you know what I mean. It's really melted ice. It's now cold water. I'm talking about changing the cold water at 0 degrees that came from the ice up to the final temperature. So that's the energy gained by the ice. It's a 2-part formula. What's the energy lost by the water? Well, the water doesn't change state. The water here stays as water. It's only its temperature changes. So that's going to be mc delta theta for W. So again, you can see the process of solving these problems. Simple diagram with all the information, energy equation in words, and then I put in the correct formula. Now, I just want to fill in the numbers. So I'll going to the center here because I need lots of room to do this. The mass of the ice, 0.08. The latent heat of fusion of ice, well, that value will be given to me. That's 3.3 by 10 to the power of 5. Plus, this is now the melted ice. Its mass doesn't change. It's still 0.08. By the SHC of water, because the ice is now water. That's 4,180. By the change in temperature of the ice. Ask yourself, what's the starting temperature of the ice? The starting temperature of the ice is 0 degrees Celsius. What's the final temperature of everything? Theta. What's the difference? Well, you know what? Theta is somewhere between 0 and 68. So to keep it positive, it's going to be theta minus 0. And theta minus 0 is just theta. On to the other side of the equation, the water, the mass of the water, 0.64. The SHC of the water, 4180. And the change in temperature of the water. The water was 68. It went down to theta. So in order to keep it positive, it is going to be 68 minus theta. Now, it's just your mathematics. Basically, you're going to multiply these numbers out, bring all your thetas to one side. It is all done in the solutions. I'm not going to show it to you here. You work on it yourself. My final answer for theta I get 51.7 degrees Celsius. So do the calculation yourself. It's not a hard calculation. You're just talking about simple algebra. But you must do it. You must practice it. As I said it, if you can't do it, it's all done in the solutions for you. Right, let's move on to the final example of this lesson, example 9. In example 9, I've got 50 grams of steam at 100 degrees Celsius. It's passed into 1.3 kilograms of water at 5 degrees Celsius. So the temperature of the water is 5 degrees Celsius. How will I introduce the steam? Well, that could be a little pipe connected to a kettle, for example, and the steam comes rushing down in there, and it's going to condense in the water. Now we have to make sure it doesn't bubble through the water and escape. That's an assumption made in all of these problems, that when the steam condenses, all of its energy goes into heating the water. None of it escapes out into the atmosphere. So you might have to put a lid on it or something like that to make sure that happens. But anyway, we're not here to worry about such details. We'll just do the problem. What happens to the water? It's at 5 degrees Celsius, and obviously it's going to get hotter. So its temperature is going to go up. And its temperature, its final temperature, that's the question. What's the final temperature? We call that theta. Put a box around that. Again, we're talking about an energy equation. Who gains? Who loses? Well, the steam is obviously going to condense back into water. So it's going to be energy lost by steam. And the water is going to get hotter. So it's energy gained by water. Theta, it's going to be somewhere, isn't it, between 5 and 100. That's important because remember when I do delta theta, I want to make sure it's always positive. So let me do the calculation. The energy lost by the steam comes in two parts. First of all, I have to change steam into water. That's a change of state. So we're talking about M by L for steam. Plus, now it's turned into boiling water at 100 degrees Celsius. I now have to change the temperature of that water. Because I'm talking about changing the temperature of something, it's going to be MC delta theta. I'm going to write down steam again. Even though it's no longer steam, it's actually the water from the steam, if you know what I mean. So that's the energy lost by the steam. And that's equal to the energy gained by the water. The energy gained by the water, well, the water doesn't change state, does it? So that's just MC delta theta for the water. So again, you see the three-part way I solve everything. I do my diagram with all the information on it. I write down my energy equation in words. Then I write down the formula. Next, I put the numbers in, and then it's just algebra. Can I do the algebra? So let's put it together. The mass of the steam is 0.05. The latent heat, and of course you've got to pick the values, the latent heat of vaporization of steam, but that's given anyway in the problem, and that's 2.3 by 10 to the power of 6. Now the next part is, this is the water that came from the steam. It's water at 100 degrees at the moment. Its mass is still 0.05. The SHC of water is 4,180. And the change in temperature of the steam. Well, ask yourself, what's the starting temperature? 100 degrees Celsius. What's the final temperature? Theta. And you know theta is somewhere between 105. So to keep it positive, take them away. It's 100 minus theta. And now the other side of the equation, the mass of the water, 1.3 by the SHC of water, 4180, by the change in temperature of the water. Keep it positive. It started at 5, it went up to theta. I keep that positive by saying that's theta minus 5. Now we're down to the algebra. And look, it's not that difficult. It looks a bit messy. But basically, you're just multiplying the numbers, multiplying out the brackets, bring all your thetas to one side. Again, it's done in the solutions. I want you to do it yourself. The answer I get for the final temperature theta I get an answer of 28.9 degrees Celsius. Okay, so they were some tricky calculations, but they'll get us ready to do all of those heat experiments later on. Anyway, that's the end of lesson 2 from chapter 2 on heat, and we'll do lesson 3 shortly. So thanks very much.